So we're going to move on to section 2.2, which is on normal distributions, which is a word I'm going to define in a little bit in a second. Distributions. So we've talked a lot about various different density curves, right? We talked about a density curve that is skewed right. We talked about a density curve that is skewed left. We've talked about various density curves that are, I don't know, symmetric, looking something like this. And we've talked about density curves that are uniform. That might be a word you might want to just remember. A density curve that looks totally flat like this is called uniform. And some other kind of wackier density curves, right, that might look something like, I don't know, like this, right? Whatever, okay? Some crazy density curve like that. Who knows what that is? We're going to talk today, the most important density curve you're going to see, which is something called the normal curve. The normal curve or the normal distribution. And the word normal we think about kind of meaning like regular or plain, but normal in the context of this class has a very specific meaning. It means a density curve that looks like this. The normal curve is the bell curve. When you think about normal curves, yes, they are certainly symmetric, and yes, they are unimodal. But certainly you could imagine some curve that is symmetric and unimodal that is not normal. For example, this one, right? This curve is symmetric and is unimodal, but is not normal. So we wouldn't call this one, this is not normal. The normal means the specific shape that I drew above the bell curve. And when let's talk about this in a little more detail because it's super duper duper important. It's certainly the most important density curve. In the middle of the density curve is the mean, which I'm going to use mu because when you talk about density curves and normal curves, you're talking about a large population, so mu makes the most sense. Somewhere there's the idea of the standard deviation sigma, and I want to talk about that in some detail because when you look at this density curve, let me make my pen a little thicker here. It's kind of going along like this, and it's actually here, it's concave up, kind of holds water. And at some point you get to a point right about here where it switches from concave up to concave down. The same thing happens over here. It's concave down. About here it switches to concave up. That point where it switches from concave up to concave down, or vice versa, is called a point of inflection. Oh boy, my pen's still thick. Hold on. Oh no. Let's try that again. It's called the point of inflection, which if you've taken calculus, you've seen that term a little bit. That's this point right here. It turns out that for a normal curve, the points of inflection, I should say, happen exactly one standard deviation away from the middle, and this is, I'm going to write -1 sigma because it's in the negative direction. That should maybe let you draw a normal curve a little bit more accurately. Because they are so important, there's a notation for normal curves, which is a big capital N. So if I write, for example, n, 110, 8. That's an 8. Trust me, that's an 8. This means the normal curve with mu equals 110 and sigma equals 8. And now we should be able to draw that somewhat accurately. The mean's got to be 110. We know a point of inflection happens 8 in each direction. So I don't know, it might look something like this, where this point of inflection would happen at 118, and over here it would happen at 102. It kind of lets you draw it more accurately. Okay? Now I picked these numbers because a lot of things actually might happen. Things in the real world end up being sort of normal. For example, you can imagine some, 8th grade class where weights of students are normally distributed. Again, this word normal, super duper important, with mu equals 110 pounds, and sigma equals 8 pounds. And things like weight and height end up kind of often being normally distributed. We've got a lot of people that weigh about the same, a few really heavy people, a few really light people. Heights, most people have about the same height, a few tall people, a few short people, kind of distributed like that. SAT scores, test scores often are normally distributed. Okay? The next thing is there's a really important rule for normal curves that lets us really think about them a lot. And it has arguably the worst named rule in the history of statistics. It's called the 68, 95, 99.7 rule. Kind of crazy, huh? And here's what this rule means. That 68% of observations are within plus or minus 1 sigma of the mean. Okay? Let me draw a picture and kind of help you see what that means. I'll use the same one I did before. So here's our density curve. Okay, it looks like this. Mu is in the middle, that's 110. We said if you go plus or minus 1 sigma, it gets you to a point of inflection. So here's 118, here's 102. What this rule tells us is if you shade in here, what percent of observations are between 102 and 118? The answer is 68%. This is a rule of thumb. It's not exactly 68%, but it's pretty darn close to 68%. Okay? The rule keeps going with the 95. 95% of observations are within plus or minus 2 sigmas, and 99.7% of observations are within plus or minus 3 sigmas. Okay, so let's talk about that a little bit more detail. Okay, 2 sigmas, well, our sigma is, in this case, our sigma is 8. So 2 sigmas would be 16. So if you go 16 away over here, you get 126. Go another 8 this way, you get, I'll do the math, 94. Good job. So if I shade here, this kind of whole dark gray area, what percent of observations are in there? Well, the answer is 95%. I'll switch to a nice kind of like yellow color here. Okay, 3 sigmas is going to be, well, sigma's 8, so it's 24. So if I go way out here, another 8 gets me to 134. Go another 8 here, it gets me to 86. Shading in this yellow region, what percent of observations are in that yellow region? Well, the answer is almost everybody, 99.7%. Okay. Let's do some kind of problems on the next page involving this rule of thumb, but it lets us really do some good thinking about it. So I'm going to draw the same normal curve again and ask you kind of a bunch of questions about it. I'm going to draw it up here. So I'm just going to use the same numbers. Okay, so I'm going to put those important numbers over here. So here's 110, that's the mean. Let's go 8, that gets me to 118. I'm not going to draw it as accurately as I did the first time. This is 126. This is 134. No, we're recording again, okay? And notice this is 1 sigma, 2 sigmas, 3 sigmas, right? Going here, we get 102. That's negative 1 sigma. This is the mean. Let's go another 8. That gets me to 90. What did we say it was? 94. And then 86. This is negative 2 sigmas. This is negative 3 sigmas. Okay. So one question you might ask yourself is, okay, let's do kind of we'll do 3 examples. Part A is what percent of observations are more than 118. Now, in case this, I kind of set up this example as like there's all 8th graders, their average, this is their weight. So you might ask this question is, what percent of 8th graders weigh more than 118 pounds or something like that? Well, here, let's think about this. What percent are in here? Well, that's between negative 1 sigma and 1 sigma. So this is going to be 68% in here, right? With the whole thing under the density curve has to be 100%. So we know that in here, the 2 tails combined, meaning this tail over here and this tail over here, have to be 32% total, because 100 minus 68 is 32%. So this area, each of these areas in here, because it's symmetric, have to be 16%. So the answer to this question is what percent or more is in 118? Well, look, the area under the density curve tells us the proportion, so the answer here is, we'll write it in red because it's so, I should write it in orange, is 16%. Okay? In terms of a notation, you could write the same problem as the probability, or the percentage, whatever you want to think of that P, that x is greater than 118 is 0.16. That notation means the same thing. Well, you'll see that notation over and over again. In fact, I'll use it in this next example. What if I asked you in part B, what percent are less than 94%, or 94 pounds, I guess I should say. Well, again, in terms of my notation, that means the probability that x is less than 94. And let's think about that a little bit. I'll do it in kind of this teal color. What percent are in between 94 and 126? Well, that's 2 sigmas. So in between here and here, we know it's going to be 95%, right? Well, it means what's left on the 2 tails, meaning here and, well, sorry, here and here, it's 5% total. So that means that each of these tails has to be 2.5%. So the answer here is what is this area right here? Well, the answer has to be 2.5%. So we get equals 0.025. And there can be some really kind of tricky problems that I'll let you kind of think about. You know, for example, let's do a kind of a crazy one. Let's ask, find the probability that, let's go, 86 is less than x is less than 110. Let's think about what that might mean. Okay? Well, 86 is 3 sigmas, and we know that 3 sigmas is 99.7%, which means the 2 tails combined, which this little tiny black regions over here, have to be 0.03 each. Sorry, 0.03 combined. So that means each one has to be, I did that wrong actually, it's not 0.3. Yes, it's 0.3%, right? Or 0.003. That's combined. So each of these little tails right here have to be 0.15% or 0.0015. So now, that's just this black tail right here. Well, how about between 86 and 110? Well, think about 110. 110 is exactly in the middle. So what's over here? Well, the answer is 50% is less than 110. So what percent's between 86 and 110? Well, you got all of 50% this way, minus this little tiny region in here. So you're going to get 0.5 minus 0.0015 gets us 0.4985. It's a good example of how you can use it to kind of use this rule, the 68, 95, 99.7 rule, to think about problems involving this.